First one, series combination of resistor and voltage division. Second one, parallel combination of resistor and current division. Third one, open and short circuit. Fourth one, problems with series parallel reduction of resistance. Next I am going to explain series resistors and voltage division. When two resistors are connected in series, the current flowing through two resistors are same, but voltage drop across each resistor is different. How to find out voltage drop for the resistance 1? From Ohm's law, V is equal to IR. In the similar manner, V1 equal to I into R1. And what is V2? V2 equal to I into R2. If we apply KVL to the loop moving clockwise direction, what is V here? When the loop is moving in a clockwise direction, V is voltage rise, V1 is drop and V2 also drop. How to write the equation? V minus V1 minus V2 equal to 0. Or we can write V is equal to V1 plus V2. What is V1? I into R1. What is V2? I into R2. From this, I is equal to V divided by R1 plus R2. Or V is equal to I into R equivalent. What is R equivalent? The summation of R1 and R2. So the equivalent resistance of any numbers of resistors are connected in series is the sum of individual resistance. Next, what is the general case? For n resistors are in series, R equivalent equal to R1 plus R2 plus Rn. To determine the voltage across each resistor is V1 equal to I into R1, V2 equal to I into R2 and I is equal to V divided by R1 plus R2. Now I have to substitute the value of I in the equation. V1 equal to V divided by R1 plus R2 into R1. V2 equal to V divided by R1 plus R2 into R2. So V1 equal to R1 by R1 plus R2 into V. V2 equal to R2 by R1 plus R2 into V. So this formula is known as voltage division technique. Here how to memorize this formula or how to remember this formula in an easy way is V1 is equal to, first put the total voltage into the same resistance divided by the total resistance R1 plus R2. In the similar manner, how to find out V2? V2 equal to the total voltage into the same resistance R2 divided by R1 plus R2. I will explain the parallel resistors and current division. When two resistors are connected in parallel, the voltage appear across two resistors are same, but the current flowing through each resistor is different. The current flowing through each resistor is find out from Ohm's law. I1 equal to the voltage V divided by R1. I2 equal to V divided by R2. Applying Kirchhoff's current law at a node A, we get I is equal to I1 plus I2 because I is the incoming current and I1 and I2 both are the outgoing currents. Incoming current should be equal to the outgoing current. Now I have to substitute the value here. I is equal to I1 plus I2, no. I1 is V by R1 plus I2 is V by R2. Take V outside. 1 by R1 plus 1 by R2 equal to V divided by R equivalent. So 1 by R equivalent is equal to 1 by R1 plus 1 by R2. From this, how we can write 1 by R equivalent? R1 plus R2 divided by R1 R2. So what is R equivalent? Inverse of this R1 R2 divided by R1 plus R2. The equivalent resistance of two parallel resistors is equal to the product of their resistance divided by their sum. When two resistors are same, R1 equal to R2 equal to R, so it is R equivalent resistance, R into R divided by 2R, that is equal to R by 2. When n numbers of resistors are connected in parallel, the equivalent resistance is 1 by R equivalent is 1 by R1 plus 1 by R2 up to 1 by Rn. So what is R equivalent? 1 the whole divided by, if all the resistances are equal, so the answer is R equivalent divided by R equivalent equal to R divided by N. Then what is V? V is I into R equivalent. I into what is R equivalent? R equivalent is R1 into R2 divided by R1 plus R2 when two resistors are connected in parallel. So I1 equal to V by R1 and I2 equal to V by R2. What I have to do, I have to substitute the value for V. So V is equal to I into R1 R2 divided by R1 into R1 plus R2. Now the R1 and R1 both are get cancelled, and finally I get I into R2 divided by R1 plus R2. In the similar manner, I1 is V by R2. What is V? V is I into R1 R2 divided by R2 into R1 plus R2. Now both the R2s are get cancelled. I get the answer I into R1 divided by R1 plus R2. How to remember this formula? I1 equal to, this is the current division technique. So I1 equal to the total current into the opposite resistance. Opposite resistance is what? R2 divided by the total resistance R1 plus R2. In the similar manner, how to find out I2? I2 equal to the total current I into the opposite resistance, that is R1 divided by R1 plus R2. Next we are going to see what is short circuit and what is open circuit. What is short circuit? Here using the copper wire, I have to shorted both the terminal. So it forms the short circuit. In a short circuit, full current is flowing because there is no resistance. Always current flowing through a low resistance path. But here what about the resistance? Resistance is equal to 0 and voltage also equal to 0. But is there any current flowing through a resistance? There is no current flowing through a resistance because current always flowing through a low resistance path. And next open circuit. Here I have to open circuited the terminal. Is there any current flowing through open circuited terminal? No. Voltage across it is infinity. That is R2 equal to infinity. Here the voltage across is the same voltages appear across this terminal. Here what is the current? The entire current is flowing through a resistance R1. So this is the open circuit. So in the short circuit, full current is flowing and resistance equal to 0. In an open circuit, current equal to 0, resistance is infinity. Next we are going to see the problem number 1 in resistance reduction technique. Find R equivalent for the circuit shown in figure. See in the circuit, we are having series and parallel combination of resistances. So first of all, step number 1, A comma B section is there. First section I am going to reduce the series combination of 1 and 5. And B section I am going to reduce the parallel combination of 6 and 3. How to reduce the series combination? By adding both. How to reduce the parallel combination? 6 into 3 divided by 6 plus 3. Okay, see the step number 1. A, 5 and 1 are connected in series, so 6 ohm. And B section 6 ohm and 3 ohm are connected in parallel. Net resistance is 6 into 3 divided by 6 plus 3, that is equal to 2 ohm. So this is a new circuit. After reducing the resistance, we get this circuit. Here 6 ohm, 2 ohm, 2 ohm, 4 and 8. So next is how to reduce this. Here 2 ohm and 2 ohm both are connected in series combination. So what is the resultant value? That is 4 ohm. Now this is the circuit that consists of reduction of both the 2 ohm resistances. And next see, here both the resistances are connected in parallel. Now I am going to reduce the resistance. 6 ohm and 4 ohm are connected in parallel. So what is the net resistance? 2.4 ohm. And this is the resistance combination. Next see, these three resistances are connected in series. So summation of these three resistances give the total resistance 14.4. So this is the final diagram. Okay, see the problem 2. Find R equivalent for the circuit shown in figure. So what you have to do, the step number 1, these three resistances are connected in series 4, 5 and 3. So what is the answer? That is 12 ohm. And next, this is the reduced circuit. And step number 2, here both 4 ohm and 12 ohm are connected in parallel. So how to reduce this? 4 into 12 divided by 4 plus 12, that is 3 ohm. Now this is the reduced circuit which consists of 3 ohm. Next in the circuit, both the 3 ohm resistances are connected in series. What is the net resistance? 6 ohm. And see, this is the final diagram. And next, step number 4, both the resistors are connected in parallel. So 6 into 6 divided by 6 plus 6, that is 3 ohm. This is a reduced network. Next, step number 5, these three resistances are connected in series. So what is the answer? 10 ohm. So this is the diagram. Next, we are going to see the problem 3. Find R equivalent for the circuit shown in figure. See, in the circuit, two sections are there. The step number 1. The first one, what we have to do, I have to take the 3 ohm resistance and the 12 ohm resistor. See, the 3 ohm resistor and 12 ohm resistor, one of the both the terminals are connected together. Okay, see, 3 ohm and 6 ohm resistance, not 12 ohm, 3 ohm and 6 ohm resistor. And here I have to take 4 ohm and 12 ohm resistor. 3 ohm and 6 ohm both are connected in parallel, resultant 2 ohm. 4 ohm and 6 ohm are 12 ohm are connected in parallel. Here both the ends are connected together. Here both the ends are connected together. So what is the resultant value? That is 3 ohm. Now this diagram that shows 12 ohm, 1 ohm, 1 ohm, 5, here 3 and 2. Reduced network. Next network, 1 and 5 are connected in series, that is connected in parallel with 3 ohm. 5 plus 1, 6 ohm. Next see, this 3 ohm and 6 ohm connected in parallel. Now we get 2 ohm. This is the reduced network. Now this 1 ohm and 2 ohm are connected in series. Again, the series connection value in parallel with 2 ohm. So 2 and 1 are connected in series first, 3 ohm. 3 ohm is in parallel with 2 ohm resistor. The net value is 1.2 ohm. And next 5, 12 ohm and 1.2 ohm are connected in series. What is the resultant value? 13.2. This is the final answer. In this way, we can reduce any type of series and parallel network problems. Thanks for watching. Have a nice day.